And if you had to calculate this limit, then you'd know that it was an indeterminate form, because you've got, like when you plug in x equals 3, you get 0 over 0. But in this case, you'd also be able to say, like, look, I can just cancel out that x minus 3, and it'll be fine. On the other hand, if you're a calculus textbook author, what you do is you just write things like this out, and then you multiply it out and just give it to the student, and then you end up making the student just have to like factor it in order to figure out like where the asymptote is. So that's how a lot of these problems are they're just created like that. So anyway, that's the first kind of limit at infinity. When you're saying like x is going to a finite limit, like x equals 3 in this case, but the y values are going to infinity. Now there's another kind of limit. There's another kind of infinite limit. I'm trying to think of a good example. There's not any obvious ones in the text, so I'll use this example that I used in my video, which is just if you look at like y equals arctan of x. You might remember from, like if you've had like an earlier math class that talked about asymptotes, you might remember that in this case there is what you call a horizontal asymptote. Should be putting that stuff in chat when I'm talking about it. So let's more screen real estate here. I need like 2 or 3 big screens. So I'm saying horizontal asymptote, and now let me chat that to everybody. And what does that mean? So the horizontal asymptote is this horizontal line, whereas the vertical asymptote was a vertical line. And that horizontal line is going to be placed, in this case, at pi over 2. And what's the reason for that? So you have a horizontal asymptote. You have a horizontal asymptote if the limit of f of x as x that goes to infinity is equal to a finite number L. And so this is something I talked about in the video. But like, so how do you know this horizontal asymptote is located at pi over 2? Go ahead and show it again here. So here's the graph of tangent. The graph of arctangent. So arctangent is kind of like inverse tangent, but there's no inverse to tangent because it doesn't pass the horizontal line test. So what you do instead is you just restrict the domain of tangent to like minus pi over 2 to x to pi over 2. And after you restrict the domain, it does pass the horizontal line test. And so tangent has this vertical asymptote at x equals pi over 2 and x equals negative pi over 2. So tangent is just sine over cosine. So when you plug in pi over 2 to cosine, you get 0. So whenever you plug in pi over 2 to tangent, you get 1 over 0 going to infinity. Same thing with negative pi over 2. So that's why you see for a tangent, you've definitely got these vertical asymptotes, these infinite limits at pi over 2. Now arctangent is the inverse function. And when you take the inverse of a function, geometrically, the way to do that is to look at the line y equals x, and then you take this and reflect it over that line. When you do that reflection, in this case, you'll see that. It's kind of cool to have it all laid out like that, like so you can really see like the mirror images coming out, like tangent in green, the line y equals x, and then arctangent. And the thing about that is that when you take an inverse function, if the original function had a vertical asymptote, then the inverse function is going to have a horizontal asymptote. So see if I can graph it for you. So the vertical asymptotes here are x equals pi over 2 and x equals minus pi over 2. You can see that. And when you take the inverse function, these are going to change to y equals pi over 2 and y equals negative pi over 2, because x and y switch when you take the inverse. And you can see that these vertical asymptotes become now horizontal asymptotes for arctangent. So the same reason that as x goes to pi over 2, tangent x goes to infinity, it's going to be true that as x goes to infinity, arctangent of x is going to go to pi over 2. So that's your other kind of infinite limit. Like as x goes to infinity, what does it mean for x to go to infinity? It means to say that as x increases without bound, arctangent of x will approach pi over 2. You could also talk about the limit as x goes to negative infinity. So in this example, as x goes to negative infinity, so the absolute value of x increases without bound, and x is negative, then the y values are going to approach negative pi over 2. So before I go off and do, like, show you a bunch of homework exercises, like, do you have any direct questions for me about any of that, any of those concepts? Okay. And just to remind you about something that we're going to use over and over and over again throughout the course, like if you have x to the n, where n is like a whole number, like 1 or 2 or 3 or 4, then your limit of x to the n as x goes to infinity is always going to be infinity. Like you can see that from the graph. Like, in fact, as n gets bigger, n doesn't even need to be a whole number. But as n gets bigger, like the graph, switches. You can see it switching from even to odd, depending on whether n is even or odd. But as n gets bigger, like this graph goes to infinity faster and faster and faster. So I mean, look at how fast it's increasing. So certainly, as your x values increase, then this is going to be going towards infinity. So as x increases, then this will go towards infinity without bound. I guess it depends on whether n was even or odd, because like if you go back to n equals 5, then, well, yeah, so sorry, yeah, for x being positive, it doesn't matter, because when x is positive, like these y values always go to infinity no matter what. But then if you compare to, like, here's n equals 9, so you can see how if you now take the limit as x goes to negative infinity, this is going to negative infinity, whereas when the exponent's even, then as x goes to negative infinity, the y values will go up towards positive infinity. So just a little thing to note. And also, if you do like 1 over x to the n, then the reverse is true, because now as x goes to infinity, the 1 over x to the n is going to 0. And that's always going to be true so long as n is bigger than 0. If you make n less than 0, then you can see it actually starts to trend upwards to infinity again for any n bigger than 0. As x gets large, the y values are going to tend towards 0. And that information is collected on page 103 if you want to refer to that. But I'll be using those facts like a lot. So let's just do some problems. So I'm in chapter 2, section 8 in the exercises on page 106, if you want to follow along with me. But you don't have to. So I'll write down some exercises and we'll just do them. So it says, like, evaluate the limit. And the first one is limit as x goes to infinity, x over x plus 9. And like, there's different ways you can do this. One way you can do is like plug it straight into Desmos and you can see the answer. Another thing you can do is, well, I mean, you can try to get an idea of like what we call the asymptotic behavior, like whether or not there's an asymptote, by imagining yourself like plugging in infinity to the function. I mean, you can't actually do that, but you can imagine, like, what if I let x increase without bound? And when you do that, you get, you get infinity over infinity. So this is the indeterminate form, infinity over infinity. So you can't necessarily just evaluate this by imagining that x is growing without bound, but this is like a fake difficulty. It doesn't really matter, because you've got a ratio of two things, and you've got x and x plus 9, so they're just offset by 9. So these two things are growing at basically the same rate. So like I expect that this limit's going to come out to 1, but let's see how to prove that. The way you might prove that is to try to not have x's on the numerator and denominator. You might try to get like your variable sort of down in either the numerator or the denominator. For me, I'm going to think maybe I can multiply and divide by 1 over x. So this is this, same mathematician's trick we've been using a few times already, is like you're multiplying by the number 1, you're multiplying and dividing by the same thing so as not to change the value of the expression. So I take the limit as x goes to infinity, meaning I'm trying to infer what is the behavior of the expression here as x grows without bound. So x over x is equal to 1. And now I've got 1 plus 9 over x. And now there's lots of ways to solve this. One way to solve it is with the limit law. Like this is going to be limit of 1 over limit of 1 plus limit of 9 over x. So this is going to be equal to 1 over 1 plus limit 9 over x. And now you see why I took some time to emphasize the fact that if you've got like 1 over x to the n, here n is equal to 1, then that's going to tend towards 0 as x tends towards infinity, right? As x is getting larger without bound, 1 over x is getting smaller and smaller, closer to 0. So you're left with 1 over 1 plus 0 equals 1. So just as expected, this is a ratio of two things that are very similar. It's just offset by 9. As x gets large, that ratio tends closer and closer to 1. But you can't immediately just use a limit law because you're going to get infinity over infinity. You have to do some algebra first to put it into a form where you can see which part's actually going to 0 and which part's really going to give you that limit. Yeah, so why did I get 1 over 1 plus 0? Because it's 1 over 1 plus the limit of 9 over x. And the limit as x goes to infinity of 9 over x is equal to 0. As x goes very, very large, then 1 over x will go very, very small. And of course, 9 over x will also go very, very small and tend towards 0. And we can also check that out on Desmos. We can also check that out. On Desmos, the function was x over x plus 9. So there's the graph. I mean, you can see a vertical asymptote at x equals 9 that we're not so interested in. We're interested in the long time behavior as x goes to infinity. And what's happening is that those y values are getting closer and closer and closer to the number 1. As you can see, losing the scale a little bit, but this is the number 1, I think, and we're creeping on up towards it. I mean, I can click on it to see a point. So yeah, you see we're up to like 0.7, and it'll take a long while to get there, but let's go out to x equals 120, and the y value is now 0.931. So as x value increases without bound, that y value is going to slowly be creeping up towards 1, even though it never gets there. And that's why it's called a limit. 1 is the limiting number. So more exercises. Let's take number 9. What we're doing on time? Yeah, we're doing just fine. So let's take limit x goes to infinity of 3x squared plus 20x. over 2x to the fourth plus 3x cubed minus 29. So part of gaining facility at mathematics is I think the idea of gaining intuition. And so what's my intuition tell me about this? I'm thinking that this is probably going to go towards 0, and that I'm thinking the limit as x goes to infinity of this is probably going to be 0. And let me explain why I have that intuition. So I see two polynomials, and one of them is a quadratic polynomial, and one of them is a fourth degree quartic polynomial. And what I'm thinking is that this expression, maybe you call it f of x, what I'm thinking is that this expression is going to travel to, this expression is going to be kind of comparable or similar to 1 over x squared. Because what I'm thinking is that as x get really, really, really large, these terms won't contribute very much, but it'll just be the largest terms in the numerator and denominator that contribute the most. And so I'm thinking that asymptotically, like in terms of asymptotes, as x goes to infinity, this function will have the same asymptote as that function, and therefore this limit will be 0. That's my intuition, so can I show it? So I just want to use this same algebra trick. I'm going to divide numerator and denominator by, this time I'll do 1 over x squared. So what I'm doing is I'm dividing by the highest power of x that I see in the numerator. And of course, I'm doing it on numerator and denominator so as not to change the value of the expression. And the reason for doing that is now everything in the numerator will have a limit, as you'll see, because I'll get 3, I'll get 20 over x. There's a limit to 3, that'll limit to 0. And then I'll be able to use the limit laws. Whereas I couldn't use the limit law here because I would just get infinity over infinity. So let's carry that through. Let's carry the algebra through. Multiplying everything through by 1 over x squared gives me 3 plus 20 over x on the numerator. And on the denominator, multiplying everything through by 1 over x squared gives me 2. X squared gives me 3x cubed over x squared, that's 3x, minus 29 over x squared. And now if so I'm trying to find the limit of this as x goes to infinity. And now I can look at this and say what's happening to the numerator, what's happening to the denominator. So the numerator is tending towards 3, because as x goes to infinity, I have 3 and I've got 20 over x, but x is getting large, 20 over x is tending towards 0. So this part is tending towards 0. And on the denominator, what's happening? Well, 29 over x squared is tending towards 0. That's true, but 2x squared plus 3x is tending towards infinity. So as x is growing large without bound, 2x squared plus 3x is also growing large without bound. So this limit this function tends towards 0. That's because the numerator is staying constant, close to 3. The denominator is growing without bound. So I've got something that's very close to 3 no matter what, divided by a number that's getting larger and larger and larger and larger, so that expression is tending towards 0. And I can't literally use a limit law to do this, because it's not like I could take limit of the numerator over limit of the denominator and then just say like 3 over infinity is equal to 0. Like, you might want to do that. Like, it kind of makes sense to think that way, but infinity is not a number, so we can't like really use the limit law. But instead, what we say is we've got like a constant over something tending towards infinity. That result tends towards 0, so the limit is actually equal to 0. So I think the language around describing that is almost more difficult than the calculation itself. And I do want to share with you, I won't do this every time, but I do want to share with you the graph so we can get like a handle on what the computer says. So what was this? It was 3x squared plus 20x divided by 2x to the 4th plus 3x cubed. Minus 29. So that's what that function looks like. And this stuff in the middle, we don't really care about. We were asked instead to look at like what's the asymptotic behavior, that is to say, to investigate the horizontal asymptotes. So what happens when x goes to infinity? So x grows large without bound. You can see we're heading towards 0 really fast. So even when x is 32, we're already 0.001. And it's just going to get closer and closer. So that 1 over 2x squared term is really doing it. Or when you phrase it this way, the 3x squared going to infinity can't beat the 2x to the 4th going to infinity. So the ratio stays close to 0. Let's look at some more problems. I mean, I should give you one to at least practice. So why don't you practice on limit as x goes to infinity of 9x squared minus 2 over 6 minus 29 times x. So see if you can evaluate what's that horizontal asymptote going to be, if any. What's that limit going to look like? Will it be finite? Will it be infinite? And let me know any questions. So after letting you think for a moment, I'll discuss. This one I won't do out in detail. It's your practice problem, but I will discuss it verbally and certainly answer any of your questions, tell you the answer. Here, I'd like to continue this principle of looking at the highest power in the numerator and then dividing by that so that I can tell what's going on. If I just look at what's happening to 9x squared minus 2 and separately look at what's happening to 6 minus 29x, I get infinity over infinity, which does not help me. That's indeterminate. I divide the numerator and denominator by x squared. I'll end up with like 9 minus 2 over x squared. So the numerator would tend towards 9 in that case. The denominator would end up with 6 over x squared minus 29 over x. And so what happens to the denominator in that case? Maybe I do actually want to write this down like a little bit. So what I do is, what you end up with dividing top and bottom by x squared, you get 9 minus 2 over x squared over 6 over x squared minus 29 over x. So as x goes to infinity, this numerator is tending towards 9 and the denominator is tending towards 0. So in this case, it looks like you're getting constant over 0. So this is going to be like an infinite limit, because if you're dividing by something that's getting closer and closer to 0, then you yourself are going to be getting closer and closer towards infinity. And whether this goes to plus infinity or minus infinity depends upon whether you're taking a right or a left-hand limit. This 6 over x squared will always be positive. And x squared gets large faster than x. So this will be positive number, but it'll be smaller than that one. So if x is positive, then I think that I expect that 29 over x will be a bigger number than this one. So you'll be subtracting something bigger from something smaller, and the denominator will be like small but negative. So actually, I think that this is straight up just going to be negative infinity. There's no, I misspoke before. There's no right hand or left hand limit when you're just saying x is going to infinity. You can't go to infinity from the right, of course. So to evaluate whether or not you're going to go to positive infinity or negative infinity, you have to look at whether this number is positive or negative. And if x squared is bigger than x, then 6 over x squared is going to be like smaller than 29 over x, if x is large enough. So this number will be negative and going to 0, and since you're dividing by it, the whole thing will go to negative infinity. So actually, that's worth a discussion. That's worth a discussion. So let's maybe see that on Desmos also. So the original function was 9x squared minus 2, and we're dividing by 6 minus 29x. So now we can like find out whether my intuition was just like a bunch of garbage or not. Check in the chat. Yeah, so what does this look like? So what does this look like? I'll zoom out a little bit, and it's kind of a cool graph. And so you can see what's starting to happen. Like as x is getting very, very large, indeed the y values are going negative. And let's plug in like the form where we divided both sides by numerator and denominator by x squared. So we get 9 minus 2 over x squared. Divided by 6 over, I mean, this is the same function, of course, but I want to prove it to you by putting it into the software. So you can see, like, it's really the same. And I want to prove to you what I said about, like, if you just look at 6 over x squared minus 29 over x, like individually, if you look at this individually, so I was asserting to you that this was negative and going to 0. And you're seeing that too. And so the reason for that is that if x squared is big, then 1 over x squared is going to be small. So x squared is bigger than x. So 1 over x squared is going to be smaller than 1 over x. So even though 29 yeah, actually the 29 helps. So 29 over x is definitely going to be bigger than 6 over x squared for most values of x, and therefore that's why you have that small negative number causing this entire thing to go to negative infinity. So yeah, so that's why infinite limits might be a little bit difficult, not because the calculations are necessarily difficult, but because you have to do this analysis where you're kind of using your intuition, you know, what's negative, what's positive, what's getting large. Back in the old days when you didn't have graphing software to check, it was much more difficult because you'd make a guess and maybe you're wrong. But now you can argue two ways. You can use your intuition, you can make guesses, and to the extent possible, you can verify with software. Of course, as you go further on in mathematics, you'll learn about the limitations of this software as well. But for the calculus class, it works really well. I want to sneak in one more problem in the remaining 4 minutes. And I hope that you do find this useful and helpful when you're doing homework. So it just says evaluate the limit. It just says evaluate the limit. But here we have a square root of 9 x to the 4th plus 3x plus 2 divided by 4x cubed plus 1. And so like once again, you've got a limit as x goes to infinity. And you can't just look at numerator and denominator separately, because numerator is going to infinity, denominator is going to infinity, and infinity over infinity is an indeterminate form. It's not an answer to a question. So what's happening, the problem is the square root. problem is the square root. What's my intuition going to tell me? Well, first of all, if the problem happened to be root 9 times x to the 4th over 4x to the 3, then I would simplify this and I'd say that's actually 3x squared over 4x cubed, and I'd say that's actually 3/4 times 1 over x. And as x goes to infinity, this certainly goes to 0. So as a mathematician, when I see a problem like this in my head, I'm making that calculation and I'm thinking, yeah, this is probably going to 0, because I've basically got x squared up here and x cubed down there. And you've got some textbook author doing some contrived, garbage, like putting a square root and adding some things to, like put this artificial conundrum in front of me. But how can I show that? How can I show that this is definitely going to 0? Like, what can I do? You want to do this trick again of like dividing by the highest power in the denominator, but you should think of the highest power in the denominator as being x squared, like because of the square root. And if you do that, like how do you bring something into the square root? So 1 over x squared is the same thing as 1 over the square root of x to the 4th, right? So if I bring this inside, I'm going to get square root of 9 x to the 4th over x to the 4th plus 3 over x cubed plus 2 over x to the 4th. So just bringing that inside, 1 over x to the 4th and distributing out. Then everything divided by 4x plus 1 over x squared. And now I can look at this, and now I can say, okay, well, now when it's written in this form for me, the limit of the numerator as x goes to infinity is 3. So this numerator really is tending towards 3. The denominator really is tending towards infinity because I'm getting x and 1 over x squared. So I'm getting something that asymptotically is looking like constant divided by huge number, which is telling me beyond the shadow of a doubt, not just with my intuition, that this is definitely heading towards 0. So that's just like how to handle those extra little wrinkles too. Of course, there's other problems and things that you can be asked. Can't do every problem in the section in an hour, but I think we've done a number of them, and we had hopefully a good discussion. So it's 12:05, and therefore class is over. It's been nice to see you all, and I will look forward to seeing you on Friday.
Thank you. Bye.